Let's do a quick 2-minute refresher on some operating systems concepts. So if you might recall, the operating system consists of two major sections, the kernel code and the user space. So the kernel code contains the core code which interacts with your bare metal hardware. It deals with process creation, it allocates memory to those processes, it keeps track of the state of the process, it reads stuff from the disk, it writes into files, it reads from files, it keeps track of what files are open, what is the file descriptor location, and it also contains device driver programs that interact with your IO devices. Everything else in the operating system is part of the user space. So all the applications that you download, Skype, Notepad, your text editors like Vim, Emacs, your Java programs that you write, your C programs that you write, your shell scripts that you write, they're all part of the user space. So your shell scripts make use of commands like ls, ps, grep. These themselves are C programs. So when you write a C program and you make a function called like fork or exec or open, where is the implementation for those functions defined? It'll be defined in some C standard library. And the most popular C standard library is glibc. So ls is a C program. It obviously has some function calls that it makes, and the definition for that is in this library. Most Linux distributions, they use this C standard library, glibc. Alpine OS is an outlier here. Alpine uses its own C standard library called Muzzle. So Muzzle has a very different implementation of the various functions. Alpine is very lightweight. It does not contain a lot of the user space programs that are in other Linux distributions. In fact, the package manager also is quite different. So you normally do sudo apt and you install some package. So apt is the package manager, which is in Ubuntu, which is in Debian. But Alpine has APK. It does not have a lot of packages in it, and the implementation is also pretty different. So Alpine is a very stripped down version of most Linux distributions, and it finds its utility in Docker. We'll see that why later. So these user space programs will ultimately have to interact with our kernel code, and they do so with the help of these system calls that the kernel exposes. So glibc under the hood makes system calls to the kernel, and then your functionality will be reflected to the hardware. Let's quickly talk about the virtual machine. So the virtual machine is basically a full-fledged emulation of an entire operating system. So it has the kernel code with all the associated functionalities of a kernel, as we saw earlier, and the user space program. So whatever programs you run on the kernel, I mean on the virtual machine, will ultimately issue some system calls, and they will be executed by the virtual machine's kernel. So if your C program issues calls to sleep or signal or wait, the kernel will execute them and change the state of the process in the P table that it maintains, the process table it maintains. If you have 10 processes inside this user space, your host kernel does not know about that. For the host kernel, the entire VM is one whole process. So let's say the host kernel allocates 10 seconds each to P1, P2, and this VM. So when this VM process gets the CPU, it is the job of the kernel's scheduler of the VM process to allocate those 10 seconds to the 10 processes running inside it. But sometimes you need to interact with the actual bare metal hardware. So for instance, let's say you create a file in the virtual machine, you save it to some location on the disk in the virtual machine, and you close your virtual machine. And if you open it tomorrow, your file is still there in that same location. So how is it actually there? Because at the end of the day, this is just a virtual machine process, and we know that processes are temporary. Whatever you save here, once this process is done executing, it'll be destroyed. It lives in the RAM. So how is it actually saved in your SSD, in your HDD? So the kernel of the virtual machine actually thinks it possesses physical hardware. And how does it think that? With the help of this hypervisor. So different operating systems will have its own hypervisor implementation. Mac OS has its own hypervisor, Windows has its own hypervisor. So the hypervisor is some software that basically provides a virtual view of the bare metal hardware to any virtual machine. So with the help of this hypervisor, the VM thinks that it owns some hardware. So when you issue system calls to the kernel will issue commands to the hypervisor, basically thinks the hypervisor is its physical infrastructure. The hypervisor in turn takes those commands, translates them into other system calls specific to this host kernel, and the host kernel will ultimately store it into the disk. So what is the takeaway from all of this? The takeaway is I want you to know what a virtual machine is, what a virtual machine contains, and an important observation is a virtual machine process is pretty big because the kernel itself handles so many important functionalities. So VM processes are pretty big. That is an important observation from this slide. Let's talk a little bit about deployment. So what does deployment mean? Deployment basically means moving your application code along with all the dependencies from your local development environment to literally any other environment, a testing environment, or it could even be the production server. And you run your application over there, and it can service requests coming from external users. So let's say you have your Java application. It is obviously composed of many different things. One is obviously the Java classes that you write, the various external libraries that you use, Spring Boot, some logging library, some database connection library, and obviously be making use of libraries provided by the Java standard library kit like java.io, java.util. And in the case of Spring Boot, if you use the Spring Boot library, it comes with an embedded server. So slight tangent here, what does a server do? A server basically exposes a port wherein you have external requests coming into that port, and this the server will manage requests coming into that port and direct it to your application. A server deals with socket creation, socket connection to those external requests. It will tie it to that port it exposed. When external users send requests to that port, it obviously is a stream of bytes. So the server will also deal with parsing those stream of bytes. It will segregate it into what is the content and what is the header. If you didn't have this, you'll have to manage all this in your own code. You'll have to manage creating a socket. You'll have to manage connection of that socket. You'll have to manage parsing the incoming request. You'll also have to manage thread pools. You'll have to manage creating threads for concurrent requests coming into your service. So all that is managed by the server. So you create a zip of this, the class along with all the dependencies, and you move this zip file from your local environment to your production environment. And the zip file from a Java context is a jar file. So you use some build tool like Maven or Gradle. It will comb through your entire repository and it will craft out what the classes are, what the dependencies are, and create a jar file. One thing to note over here is what is not included in the jar file. This one is not included in the jar file. The standard libraries of Java, they are not included in the jar file. So if you use system.out.println, the implementation of println won't be in your jar file. So where will it be? That will be part of the JRE environment. So if you're aware, we have JDK, and a subcomponent of JDK is JRE. So JRE will contain the standard Java libraries, their implementations. JDK on top of JRE will contain the Java C compiler and some debugging tools. So if you're moving your code from the local environment to the production environment most likely will just have JRE, not JDK, because you just want to run the code. You don't want to develop the code. You don't want to compile the code. Your jar file will already have the compiled code. So there's no need of having JDK in the prod. You can just have JRE. So because your JRE already contains the standard library, there's no point zipping it into your jar file. So let's say we developed our application using Java 8 and our JRE version is also version 8. All good so far. 1 year passes, 2 year passes, 3 years pass. And let's say we decide to add some new functionality into our application. And alongside with it, we decide to upgrade our Java versions. A lot has changed since then. Let's say we decide to go with Java 24. Now, a lot has changed from Java 8 to 24. In fact, in Java 21, you don't even need the PSVM, public static void main. So let's say you create your application using Java 24 in your local JDK 24 version. You create a jar file out of it and you ship it to the production environment. And the production environment, mind you, still has JRE version 8. Do you think this will be compatible with our Java 24 code? No, it won't. Our code won't run. So the fix is pretty simple. The fix is to individually go to that production environment, remove that GRE v8 and install GRE v24. Sounds trivial. But what if we have Python code as well and Golang code as well as part of our projects? So we have a Python project, we have a Golang project, we have a Java project. So now we have three things to worry about. We have three dependencies, three different things to track basically. This will be feasible in a very small scale, but let's say we decide to ship our jar file to multiple different production environments for basically better load balancing. So if you ship it to 10 different production environments, and each of those prod environments will have three projects, your Python, Golang, and your Java project, then you have 30 different things to track. So it really doesn't make sense, and it's very suboptimal to go with this approach. So it would be better if we had some kind of a sandbox where you have your jar file in whatever version, you have your GRE compatible with that jar file, the Java code that you wrote, and you also have a very minimal set of user space programs like ls, like cat or ps. Why this? We'll see in a bit. So this is the segue for Docker. So using this picture as a reference, you might infer that Docker is basically a sandbox containing your jar file, the runtime tools to support and run that jar file like GRE, and something called the minimal user program space like ls, cat, ps programs. Why do we have this? We'll get into it in a short bit. Now, this might look like a virtual machine, but it's not. If you recall from the first slide, a virtual machine contains this along with the kernel code. Docker, when you create a Docker image is a term we'll get into in a short bit. When you create a Docker image, you don't have any kernel space here. You'll create a Docker image out of some operating system like Linux, some version of Linux, like Alpine or Ubuntu. But when you create it, you will not be importing the kernel. It's just the user space programs, that to a very trivial amount of programs. So Docker is not a VM. It makes use of the host's kernel and it contains the minimal user space provided by the base image like Alpine or Ubuntu. So when you create a Docker image, you'll be specifying what base image of some operating system that you want, either Alpine or Ubuntu, and then you'll get Alpine's user programs or Ubuntu's user programs. So if you also recall, Ubuntu uses glibc standard library while Alpine uses the muscle library. So your jar file is going to be run by GRE. Your GRE JVM is written using C, C++. So they're obviously going to be using your glibc or your muscle to get the implementation for open, read, write, fork, whatever. So it's very important that if you use Alpine OS as a base image, if this is Alpine, your GRE should also be compatible with Alpine. If you're using Ubuntu, your GRE should also be compatible with Ubuntu. Your GRE should be compatible with glibc. So what does Docker essentially do? Main reason why we use Docker is reproducible builds irrespective of the system. So tomorrow, if you want to ship your Java version 24 code to some production server, you don't have to worry about manually configuring that production server to run Java 24. You don't have to change the JDK. You don't have to change the GRE. In fact, it doesn't even have to have JDK or GRE. What you need to worry about is just setting up this sandbox, dunking the right version of JDK GRE, your Java file, and the minimal user space programs, which is already part of the base image that you'll be importing. So when you essentially run this on the server, your GRE JDK will be calling your minimal user space programs, lscat, ps, glibc. glibc in turn will be making system calls to the host kernel. So the flow is your GRE will be running this. GRE makes also use of the glibc library or muscle library part of this Alpine OS or Ubuntu OS that you import. Alpine OS or Ubuntu OS in turn will be making system calls to the host kernel to eventually run your code, to talk to the disk, to make hardware specific calls. So there are three concepts specific to Docker: Docker file, Docker image, which we just mentioned, and Docker container. What is a Docker file? Docker file is used to create the Docker image. What is a Docker image? It's used to create containers. So think of Docker image as like your Java class, and the container is basically the object. So containers are basically instances of the image. They are runtime instances. They actually have memory and all. Image basically specifies the behavior of what a container should be, exactly similar to a Java class and a Java object. Now, in order to create the Docker image, we have to specify what the jar file is, what JDK versions there are, what base OS version you want to use. Do you want to use Alpine or do you want to use Ubuntu, Debian? So in order to specify that, we use the Docker file. So let's see what the Docker file contains. So the Docker file is basically used to build the Docker image. Once you have the Docker image, which is basically a file, you will ship this file to the various computers, which are your production computers, your production servers, and you will run this Docker image on your production servers. Running the Docker image will basically create a running instance of Docker, and that running instance is called Docker container. Inside your Docker container, you will have your Java code, and that Java code will be executed in that machine. So what does a Docker file have? The Docker file will initially contain the base image. It could be Alpine OS, it could be Ubuntu OS. Along with that, it'll be containing the respective JDK version compatible with that base image. So JDK, so grab Alpine along with JDK, which is compatible with muscle library. Grab JDK, which is compatible with glibc if you're using Ubuntu as a base image. So you'll specify that over here. Work directory, you will specify what the basically root directory is for this Docker container, and you will copy your jar file from your local computer. It's in under target, it could be under any folder. You will copy it from your local directory to app.jar, which is under /app. So now once you do this in the Docker container, you will have basically folders, and under the app folder you'll have your jar file. You then specify what the entry point for your application is. So you have your Docker image generated, and when you run the Docker image, it generates a running instance of Docker, which is a Docker container. Now this Docker container ultimately should run the Java code, but how does it know what to run, where to run? So we'll specify that over here. So the entry point will be this command. So when you run when you run the Docker image, run this code in the container. So java-jar app.jar, which is under /app. I also mentioned that the user space programs, apart from containing the C standard library, will have programs for ls, cat, ps, echo. Why do we need them? Where do we need them? We'll need them over here, entry point. If you want your entry point to be a little bit more than this, basically don't just run the Java application right away. Do some things beforehand. For example, open your database connection, create some logging path, and only then run your Java application. You will create a shell script for that as your entry point. So your entry point can basically be a shell script. This shell script, you will specify the location of the Docker file. So in the image, when you run the image, the entry point, you will execute that shell script. So this is a sample shell script. The shell script will have a connection to some Postgres DB. You will specify the host, the port number as part of the runtime variables. Once you're connected to the database, you will have to pick a suitable configuration file. So what do I mean by a configuration file? So let's say, depending on the pod, if it's a testing pod or if it's a production pod, you'll have different database usernames, passwords. You'll have different amount of threads to be created depending on the pod. So all those variables, those key values will be in a configuration file like app prod.properties or app dev.properties. So when you create your Docker file, If you have configuration files, you will specify that all these configuration files, prod dev, will be under the configs folder. So /app/configs or /configs or whatever folder you want to give it, you'll specify the location. Your Docker file should contain all the configuration files for the different pods. When you run the shell script, you can choose, depending on the environment, which config file to load. So you load that and dunk it in this particular folder in docker/app application.properties. So then when you run the Java code, your Java code will basically read the file which is located in this path in /app/application.properties, and it'll start executing code with the configuration variables that you've provided. So to summarize, Docker is not a virtual machine. It makes use of the host's kernel. It provides you with a basically container that contains your Java application code, your dependencies to support running that code, and the minimal user space programs like ls, cat, ps, and the C standard library. All these are provided when you import Alpine, when you import Ubuntu as a base image. It does not contain the kernel when you import it. So it's a very minimal operating system without the kernel space. And yeah, the most important functionality of Docker is that you have reproducible builds irrespective of the system. So if you can run you don't have to worry about running a specific Java version on a system. As long as you create a container that supports the dependencies, this can be run anywhere on any system. Finally, Docker is also called a containerization tool. So basically, you're just creating a container with these things dumped in it. So Docker is a containerization tool. That's another keyword here. Let's move to monoliths. So I won't spend much time here because it's pretty trivial. So a monolithic application is basically one jar file, one deployable unit that contains end-to-end the complete functionality of your business, that contains the entire application code. So you don't have different modules running on different computers. Everything is packed and wrapped under the same bundle, under the same jar file. So everything from receiving the order to processing the order to inventory to payments, all that, they might be in different packages, but they'll all be wrapped in the same jar file. So obviously a monolith will support a rapid 0 to 1 development. If you are a totally brand new business and you have to create something 0 to 1 pretty quickly, monoliths make more sense over here, because if you have a microservice for order creation, for payments, for booking, for reservation, those are each one of them is a separate pipeline. You have to worry about deploying them, testing them. You'll have to worry about individual servers for each one of them, and it's pretty cumbersome. So it makes more sense to just worry about one pipeline, one artifact. That's more easier. Simpler deployment for that same reason, and easier debugging because the whole thing runs on one server. Your logs will be generated in that same server. You don't have to worry about distributed logging. Half your logs won't be in one computer, the other half won't be in the other computer. The entire logging will be on the same node. So it's pretty easier to debug as well. Let's go into the downsides. Tight coupling. This might not always be a downside, but it might not be a downside if you employ good software engineering principles, if you maintain good object-oriented standards, but it's pretty easy to have tight coupling because the entire thing is in one unit. So what are the downsides of tight coupling? If you make one change in some file, it can cause cascading changes to related files that are tied to it. This is not that big of an issue in microservices because an entire microservice is its own sandbox. So you won't have much tight coupling there. And scalability limits. So let's say you have 5 modules in your monolithic application, A, B, C, D, E, and let's say B, C, D, E modules are very lightweight. They don't require much CPU, but module A is very CPU intensive. Now, if you want to scale your application, you will have to basically add in more CPU. And if you add in a bigger size CPU, you still have modules B, C, D, E eating from that CPU. So module A won't get 100% CPU utilization over here. So it would be ideal if we were to separate out module A and give it a brand new computer with a very good CPU, and let's separate out B, C, D, E, allocate it to a smaller computer with a smaller CPU. That should be sufficient, but that is not possible with monolithic applications. Scalability limits are are hogged by modules which require not as many resources as modules that do require them. Another downside to monoliths is slower development at scale. So if you have 4 modules in your system, A, B, C, D, and modules A, B, C are already done, but module D is going to take 2 more months to complete. You're forced to wait for 2 months before you create your jar file. So that can be a problem. Another downside related to tight coupling is, what if in one module you have a bug? Let's say one portion of your code, one portion of your module takes up a lot of memory. It creates a Stack Overflow error. In that case, your entire application shuts down, your entire application crashes because of that one bug in that one module. It's not isolated, it's tightly coupled. So, because of the capsule like nature, so because all the modules are wrapped under this one capsule in monoliths, any small bug in one portion of the code can impact the entire application. Coming to microservices, the cons over here are the pros there, the pros here are the cons there. So rapid 0 to 1 is not possible in a microservice because you have these different microservices to worry about, different pipelines, they can be written in different languages. So different tools, different process for each one of them. So deployment is going to be non-trivial in nature. Debugging also is not going to be easy because you have these services across different computers, each generating their different logs. So you'll have to individually go through to these different nodes, grab the logs, and find out the issue. There's no tight coupling over here. Basically, each service is its own sandbox. So if there's an issue in one service, you can just shut that service down. It should not impact the other services. The entire application does not shut down. So if you are running, let's say, Book My Show, and your booking service has a bug, you can just shut that booking service down. But your lookup service, if you just want to look at events, you can do that, but you just can't book events. So your entire application is not shut down. Only portions of it are. Scalability limits. So you can add more CPU, you can add more storage to the microservice depending on its usage, and you can rest assured that the entire resource will be utilized by that service alone. It won't be hogged by services that don't require as much utility. Slower development at scale won't be a problem over here because you have these different projects, different modules. Each team can develop at their own speed. They have their own pipelines to worry about. Now that we've taken a look at all this, let's finally see what exactly a distributed system is. And we'll also address in a short while, can a monolithic service, a monolithic application, ever be part of a distributed system? So literature has multiple definitions for what constitutes a distributed system. I listed 2 over here. The first one says a distributed system refers to one where you have multiple components located on different computers and they interact with each other over the network to achieve a common goal. Definition 2 says a distributed system is a collection of independent nodes that appear to the user as a single system. So I went through multiple similar definitions and I wasn't exactly clear on the understanding. It left a lot of questions. And I even went through quite a few examples of what is a distributed system, what seems to be a distributed system, to finally get at least somewhat of an understanding. And I'll tell you what my criteria is for what constitutes a distributed system in a while. So we have this setup over here. You have your client, you have one monolithic application, and you have your database. Now, going by the definition, this certainly should be a distributed system because you do have multiple components located on different computers. This is one computer, second, third computer, and they interact with each other over the network. But this apparently is not a distributed system. In the second one, you have the same monolithic application. Let's say you created a jar file, pushed it into Docker, and you've deployed that Docker container across multiple different physical computers. So yes, a monolithic application can be a distributed system. So a distributed system can contain solely of your monolithic applications. So you've scaled it horizontally like this. So the same application is across 3 computers. You have a load balancer distributing requests to one of the 3, and they are all tied to the same database. Now this seems to be a distributed system. If you look at this one, you have basically 3 microservices. Same setup, and each microservice here has its own DB. This again is a distributed service. If you look at this example, You have one monolithic application, one database that it's tied to, just talks to one DB. But this DB has two replicas. Is this a distributed system? Technically, on paper, it is, but it is not a complete distributed system. Don't worry, I'll revisit these examples when I tell you my criteria of what these distributed systems are. This is the last example. You have three modules. Let's think of it as one microservice. Once this is done, the processing should go to this module. Once this is done, the processing should go to this module. So each of them can be scaled independently vertically. You can add more CPU, more disk here, more CPU, more disk here, so on and so forth. And finally, they interact with one DB. Is this a microservice? It is. So my criteria for what constitutes a distributed system is as such, and this is going to be my definition. If your system consists of multiple components located across different physical nodes and connecting or interacting with each other through the network, in addition, you either have this point one, either the application layer consists of multiple nodes, it is most definitely distributed. If it only contains point one, it is most definitely distributed. If it contains point two or three, or two and or three, then it is partially distributed in nature. So again, if you have multiple nodes located across physical servers interacting over the network, and the application layer consists of multiple nodes themselves, it's definitely distributed. But let's say you have multiple nodes, maybe multiple DB nodes, but you just have one application layer node. Then because you have multiple DB nodes, either because you're implementing replication or you're implementing partitioning, then the system is again distributed in nature, but not completely. Let's talk about one pattern that is commonly used in distributed systems. It's called CQRS. C stands for command, Q is query, R is request, and S is segregation. So let's assume you have two tables. One is employee, the other is department. Employee has the name and the department ID. Department has the department ID and the cost center and other details associated with the department. Now let's say we have 100 records here, 100 employees and 5 departments. And let's say each employee will be tied to 5 departments. That is not a practical use case. I couldn't think of a better example. So let's say for the worst case, each employee is tied to 5 departments. Now, let's say the query commands, I mean your query requests, your read requests are very frequent in nature. And when you read, you won't be reading just the employee. You also are concerned with the employee department combination. So when you read, you might read something like select employee along with the department information that they're tied. So if you're reading for one employee, you expect 5 records to be returned. So these joins are pretty costly, especially when you are dealing with reads at scale. So it makes more sense to denormalize the data. So denormalizing means basically joining tables, creating a new table consisting of joins of smaller tables, and you're creating these denormalized tables, especially to speeden up or optimize read queries when they come in at scale. So your denormalized table will have 500 rows. And let's say writes to the system won't be as common. And so you have the one DB, the same DB will have the employee table, the department table, and the denormalized table. So assume you get 10 writes a day and you get a million reads. So this is the setup. But what if your denormalized tables is about a million rows? It might not fit into this particular table. In fact, what if you have a million reads and then those 5 writes that come, those 5 writes will have to wait a long time because reads require locks. And when you read, you'll have shared locks, but those writes will also need to grab the lock. And because you have a million different concurrent reads to worry about, chances are that those writes will have to wait for a long time to be able to update data. So in comes CQRS pattern. Q stands for query, basically all your read requests. C stands for command, which is all your update and write requests. So you're separating the query, your reads from your writes. You're segregating them. How are we doing that? So we have different pathways for read, you have different pathways for query, and you have different pathways for command. By command, I mean write or update. So let's assign a separate DB for query. So you have your 10 million reads, they can go to this DB, and because it's 10 million, you'll have 10 million requests. Maybe 1 DB might not be sufficient to respond to all of them. You can have multiple replicas of the DB. You can have multiple replicas of the query as well. You can have multiple services here. You can horizontally scale it. Similarly, because command is pretty low intensive, you can just have one DB for it, which is your original normalized DB. So there's maybe no need to create multiple replicas, just one replica for fallback is enough. So this is called CQRS. Rather than tying the entire denormalized and normalized data together and servicing both read and write requests from the same DB, which might not be efficient when we deal with scale, we used this pattern. Before we take a look at the second distributed systems pattern, let us take a look at this use case. So assume you are a vacation planning and vacation booking company. So given a request by the customer, you will book their flights, their hotels, their cars and send the information back to the customer. So assume you have three different services for them. You will book the flight, but you won't commit the flight booking status into the DB just yet. Because if you're unable to book a hotel or if you're unable to book a car, the entire vacation is ruined. So you won't be booking the flight or the hotel or the car if any one of them fails. So let's say in flight booking service, you update the status of the flight's seat to booked. But before committing it into the database, you send a request to the hotel booking service to book a specific hotel. Let's say you're able to do that and hotel interacts with car, you're able to rent the car. So hotel gets an acknowledgement from car that car rental service was able to book a car. Now hotel will commit its local transaction. It sends a success to the flight booking service and the flight booking service will commit its local transaction into the DB. So the flight booking service for that particular flight seat record in the table will grab a lock and will hold that lock until it hears back from the hotel booking service. So you'll typically use 2PC rather than 1PC for this. In fact, you'll actually use 3PC if you're concerned about messages getting lost in between. But let's go with 2PC, two-phase commit. It consists of a query phase, then hotel booking service will say if it's a success or a failure. If it's a success, you will send them a commit message and then they'll respond with the commit status if it's committed successfully or not. So you see 4 different messages going over here across the network and you have multiple nodes. So this can be pretty cumbersome. This can choke the network when you talk about scale. And especially when you talk about locks, because flight booking service and hotel and car, they'll all hold locks over the records that are specific to the transaction that you're dealing with. And they'll grab the lock until they're forced to abort or they'll commit their transaction. And it'll take a while until they commit their transaction. Up until that time, for however long it takes, they'll hold the lock to the record. What's the issue with holding locks? What if you get read requests for that specific record? Those read requests can't be serviced. Those read requests, those read threads, they'll have to wait. More the amount of threads that wait, threads consume memory and they'll start depleting the system resources. So you would never want to grab locks and hold on to them for a very long period of time. So using two-phase commit for this use case is not very optimal. So in comes the Saga pattern. Saga, the full form is segregated access for global atomicity. So global atomicity, you have these distributed transactions, but from a macroscopic view, it's one global transaction and you want this to be globally atomic in nature. All pass or none pass. So one way of implementing the Saga pattern is with the help of a central orchestrator. So there is no locks being held for a long period of time over here. So flight booking service tells the orchestrator it wants to book hotel XYZ. Central orchestrator forwards that message to the hotel. Once flight booking service submits that request to central orchestrator, flight booking service will commit its local transaction. Even without hearing whether hotel booking service passed or failed, even without hearing whether car rental service passed or failed, flight booking service, after sending the book hotel message to the central orchestrator, will immediately commit its local transaction. Same thing for hotel, same thing for car rental. Now let's say car rental fails. So it sends that message to the orchestrator. Now because car rental failed, the orchestrator now needs to tell the hotel booking service that car rental service failed. But the hotel booking service has already committed its local transaction. Now there's no way to roll back that transaction. It's committed already. So how do you undo your changes? So hotel booking service, along with the operation it's going to define, should also define an undo operation. And the central orchestrator will already have knowledge of what the operations are and what the undo operation is. So if the central orchestrator knows that car rental failed, central orchestrator will call the undo operation for the hotel booking service and it'll execute that and commit it. Central orchestrator will then move backwards and do the same thing for the flight booking service. It'll call the undo operation for the flight booking service. Another way to implement Saga pattern is with the help of the choreography principle. So you have the same flight booking and car rental service, and they will interact with each other asynchronously. What do I mean by asynchronous? So when you talk of synchronous interaction, if you submit a request from A to B, that request is handled immediately. In asynchronous, it may or may not be handled immediately. There might be some delay associated. So that is asynchronous in nature. It can be handled in the background. It can be handled when B is free. Whenever B is free, can pick up that event and process it. So flight service will submit the book hotel event to the hotel booking service. Hotel booking service is going to read that event from the event channel. The once it does, it books the hotel, it commits it, and then sends a book car for user ID 1003 event, and car rental will then read it, commit it, and that's the end of the transaction. Let's say your hotel booking service is unable to book the hotel for user with ID 1003. In that case, it submits a failure event. It submits a failure event backwards to flight service. So flight service will establish a specific failure queue and will be reading failures from that queue. So hotel booking will send an undo message, basically an undo event saying cancel flight for user with ID 1003. So it is the duty of the flight service to read from that failure queue, to read those messages and to understand what those messages mean. So when hotel booking says cancel flight for 1003, flight service should know exactly what it means. And flight service will then execute that message and commit that transaction. In effect, it basically undoes what it previously did. So your transaction is rolled back, not technically, but with the help of this undo, it is able to roll back transactions. And that's how you implement distributed transactions using the Saga pattern. Let's quickly talk about the CAP theorem before we end the video with a short segment on Kubernetes. So CAP basically stands for consistency, availability, and partition tolerance. It's a theorem that states that in a distributed system, we can achieve at max 2 out of 3 of these properties and not all 3. Let's see why. So take a look at this distributed system right here. Assume we have an application server and 2 databases, and these databases will have the same state, XS5 and XS5. Now, if I make a write to DB1, I push XS6, DB1 will replicate that to DB2, XS6, and now both the states will be XS6, so they'll be in a consistent state. So in this case, it might seem that your application is consistent. See, at any point in time, if a read goes to DB1 and DB2, that read will get XS6. Is your system available? So what does available mean? Availability basically means that any request that goes to a node which is alive and running, that request won't be rejected. You won't explicitly reject requests. So over here, your app is sending XS6 and DB1 is gracefully accepting it. It's not rejecting it. So your system is available as well. What does P mean? P means partition tolerance. Partition tolerance is very critical in a distributed system. So you have this link between DB1 and DB2, and let's assume you have a partition over here. So partition tolerance means if you have a network breakage between any 2 nodes in your distributed system, does the system as a whole still is it still up and running? Does it still accept requests? Does it still send responses? So over here, it might seem that the system as a whole is still up and running. So if the link between DB1 and DB2 breaks and app gets a request from some client to update XS6, app can just send it to DB1 or app can send it to DB2. But because the link broke over here, so there is no scope of replicating the changes from DB1 to DB2. In this case, you lose consistency if you opt for partition tolerance and availability. Let's say you don't want partition tolerance. In that case, if you erase P, the system will always be consistent, you'll always have replication, and the system will always be available. So any request that app sends to DB1 or DB2, these nodes will gracefully accept it. They won't reject requests. But you should also ensure that this link will always be alive, and there is absolutely no scope of any link breakages between any two nodes in the distributed system. But this is practically and for all intents and purposes totally unrealistic, because in any distributed system, in any real life system, there's always scope for link breakages between two nodes. Either the message can be dropped, message can be lost because of weather conditions. Let's say the input buffer at the DB2 node, that can be full and it'll stop accepting requests and start dropping them. So there can be numerous cases. The router at DB1 can malfunction and can't send requests to other nodes. So there can be numerous instances where there will be partitions between any two nodes. So for any distributed system, the P is a non-negotiable. So because partition tolerance is inevitable, we have to make a trade-off either between C or between A. So let's assume that this link breaks. Now, because this link breaks, let's say I still want the system to be very consistent. Now that this link broke and I'm sending X6. Now, if I write X6 here, there's no way to send X6 to DB2. So in that case, the system won't be consistent, but I want it to be consistent. So what will I do? When app sends X6 to DB1, DB1, even though it's alive and running, will reject X6. It will reject that write. So it will not be available. The system is not available for all operations. So in this case, it'll be X5 in both nodes. I am sacrificing availability for consistency in this case. Now let's say for some applications, I want availability more than consistency. In that case, what do? In that case, DB1, when it gets X6, will gracefully overwrite its data to X6. And the other node DB2 will still be in X5 state, so it won't be in a consistent state. So I hope with this example, you could understand what CAP is, why it's not feasible to achieve all three, and why it's absolutely critical to have P at all times in a distributed system. Let's talk about Kubernetes. Let's end this video with a short segment on Kubernetes. So you've Dockerized your Java application and you know for certain that your application is going to get a lot of traffic. So assume you have 10 servers in your setup and you want to deploy your application to 3 servers. So you have to individually go and deploy your Docker image to these 3 servers. That's point 1. Point 2, let's say in computer 1, your Docker process shuts down for some reason. Then it's your duty to restart that process on that computer. Point 3, what if a computer shuts down, an entire server shuts down? Then it's your duty to find an alternate server which is free and spin a new Docker instance on that container so that you'll have 3 replicas at all points. Now this gets pretty cumbersome with scale. So imagine if you have 100 instances to deploy. So those are 100 different things to track. And luckily for us, it is all managed by an orchestration framework called Kubernetes. So Kubernetes is an orchestration framework. Kubernetes orchestrates or manages our containers. It by itself deals with scaling, with restarting processes, monitoring the health, and ensuring that our system is always in a desired state. I'll go over these points in just a second. So this is a very high level view of Kubernetes. We have 2 core components. One is the control plane or the master node and the individual servers where our Docker instances run. The Docker instance will be tracked by an agent of Kubernetes, the worker node of Kubernetes called kubelet. So the master node is called the control plane and the worker nodes are called kubelets. So kubelets will in a way run our Docker instance, will track if the instance is running or not. If it's not running, it will restart the instance. If the entire node is down, the control plane will know that. The control plane keeps interacting with the kubelet to track the state. And if the control plane finds that a node is down, the control plane will find another node in the cluster, Kubernetes cluster, to run that instance. So control plane will deal with restarting the instance on another node. This is if the entire node shuts down. But what if the process in a node shuts down? Then kubelet will deal with it. So if a process in a node shuts down, it needs to be restarted. Kubelet will deal with it. But if the entire node shuts down, the control plane will deal with it. The control plane will spin a new instance of that Docker on another node. So it'll always ensure a desired state and it'll deal with scaling. So your kubelet will keep updating the control plane with the CPU usage, with the disk usage, the memory usage. And if the control plane feels that there's a lot of load on the system, it'll basically spin new instances on whatever clusters are, whatever nodes are available in the Kubernetes cluster. That'll all be managed by the control plane and be done automatically. And what is the last part? It says ensures desired state. So you have your development computer over here, and you have created a Docker image right here with some Docker file. Now, in order to deploy this Docker image to these instances, you will be making use of Kubernetes. So the control plane will expose some API endpoints. You just like you create a Docker file for Docker, for Kubernetes, you will specify a configuration file, and this configuration file will specify what your desired state should be. By that, I mean, what are the minimum amount of instances you want? In this case, it could be 3 or 4. What should be the minimum CPU usage? What is the minimum memory requirement? And obviously, what is the Docker image? So you'll also plug in the Docker image in that configuration file, and you'll ship it to that control plane via the endpoint that it exposes. So the control plane at all points in time will ensure that what you plugged in will always be honored with the help of the kubelets. So it keeps interacting with the kubelets, keeps tracking the state, saves the state in a database called etcd, which I won't go into this video. It under the hood uses a consensus algorithm like Raft, because it doesn't make sense to just have one control plane. What if this control plane shuts down? So you need to have redundancies. So you'll have multiple control planes, and they all need to be in sync with each other. They need to be in consensus with what the current valid state is. So it makes use of a consensus algorithm like Raft, and the database over here is etcd, which I won't be going into detail. So this is basically a high-level picture of Kubernetes. It orchestrates your Docker containers, deals with scaling, deals with restarting, manages the containers for you, and you can specify what your desired state is at the time of deployment. In the next video, let's talk about indexing.